All right, here we go. Now we're recording. All right, let's go get our textbook here. All right, so section 6.5. We were working with percents 2 days ago. And in 6.5, we're going to work with percent increase or decrease and also discounts, okay? Oftentimes you say, you know, we hear the phrase like there was a 3% increase in the gas price, or you know, a 5% decrease in our wages, unfortunately. So we're going to work with percent increase and percent decrease, and also with discounts in section 6.5. Okay. All right, now. All right, so ladies and gentlemen, here's what we're going to do here. I'm going to show you how to, in general, handle percent increase and decrease problems. Okay, so this is section 6.5. All right. If A is a starting value or an initial value of something, and let's say there is a P% increase from our initial value A to a new value of B. Okay. All right. So ladies and gentlemen, we go from an initial value A to a final value of B. And let's say there is a P% increase in taking us from A to B. Then what we can say is this. We can say the new value B is really equal to 100 plus P% of the original or old value A. There you go. So if we start with some initial value A and we experience a P% increase from A to some new value B, we can then conclude that B is equal to 100 plus P% of A. Okay. All righty. Let me give you an example here. Suppose that we're making, I don't know, you know, let's say maybe like $15 an hour at a job, okay? And let's say, ladies and gentlemen, there is a 5% increase in our wage. Question is, what is our new wage? So we start off with a $15 per hour wage, and suppose we experience a 5% increase in our wage. What would be the new value of our wage? You know, how much are we going to be making after that 5% increase? Well, ladies and gentlemen, the new wage we're going to be making is like our B. It's the new value we're going to. Our new wage, therefore, would be equal to 100 plus 5% of our old wage, which is $15 per hour. There you go. That's how you would compute your new wage. So the new wage is going to be equal to really what? What's 100 plus 5? So our new wage is really going to be 105%. of our old wage or initial wage, which is $15 per hour. Now, how do we take 105% of 15? We change the percent to a decimal by shifting the decimal point 2 places to the left, dropping the percent symbol. So it's going to be, our new wage is going to be 1.05 times $15 per hour. You got a calculator? What is 1.05 times $15 per hour? Go ahead and dial it up with your calculator. What is it?
75.
Okay, I don't know, you're coming through kind of garbled. I hope I'm not coming through garbled. 1.05 times 15. 1575, I think I heard. Okay, I heard that. So we will be making $15.75 per what hour, ladies and gentlemen, if there's a 5% increase in our wages. Does it make sense how we computed the new wage? All right. What if we have a percent decrease instead of a percent increase? I'm going to show you how that works, okay? And then we'll go off on our textbook and do several examples of each. All right, any questions about what we did here so far? We're learning about percent increase or decrease so far in section 6.5. Okay, suppose A is the initial value in something, whatever it is, and there is a P% decrease, not increase, but decrease. From A to a new value of B. Well, then we can conclude this. Then it must be true then that our new value B is equal to 100 minus P% of the initial value A. That's how you deal with percent decrease. So I want you to contrast that with our percent increase formula there. See the difference here? Percent increase is 100 plus P% of the original value for the new value. If you have a P% decrease from an original value A to a new value B, then the new value B is 100 minus P% of the original value A. See the difference between the formulas? It's pretty easy to remember because percent increase means plus, percent decrease means what? Subtraction, correct? We're decreasing. All right. Okay, so let's look at an example of a decrease problem here and try to apply that. So we're going to look at a percent decrease problem. Okay, let's take a look. Suppose there are, let's say, 1,000 employees at a plant, but the plant experiences a 10% decrease in their employees. The question is, how many employees work at the plant after the decrease? All right, ladies and gentlemen, so we start off with 1,000 employees at a plant, but then there's a 10% decrease in the workforce. How many employees now will work at the plant after this decrease? Well, we don't know how many people are going to be working on the plant after the decrease, so we'll call it the new number of employees in general. New number of employees is equal to what percent of the original number of employees? Well, it'll be 100 minus 10% of the original number of employees, which is 1,000. And that's how we're going to compute how many employees remain at the plant after the 10% decrease. So this means the number of employees remaining at the plant is going to be 90% of the original number of members, which is 1,000. Now, what's 90% of 1,000? Well, that's going to be 0.90 times what? 1,000. And what would that give you there? That's going to give you 900 what? Employees remain after the 10% decrease, okay? So 900 employees remain. So now I've shown you a classic example of a percent increase and a percent decrease problem. Now I think we can go into our textbook and maybe do a couple of more, okay? All right, let me know when you're ready to move on. Okay, are we ready to move on, ladies and gentlemen?
Mm-hmm.
All right, let's go to our textbook now. Let's go back to section 6.5 and let's try to dial up some problems. So I'm going to go right down to our exercise set, which is exercise set 6.5. And let's see if we can begin to dig into a couple of these word problems here. All right, ladies and gentlemen, number 2, a computer programmer's yearly income is $57,000, which experiences an 8% increase. What is the dollar amount of the increase and what is her new salary? So, ladies and gentlemen, how are we going to compute the new salary for number 2? The new salary is going to be equal to what of the old salary, $57,000? Is it going to be 100 plus 8% or 100 minus 8%?
Plus.
100 plus 8%. So the new salary, okay, the new salary is going to be 100 plus 8% of the old salary, which is $57,000. This is to say that the new salary is going to be 108% of the old salary, which is $57,000. How do you take 108% of 57,000? Change the percent to a decimal, shifting the decimal point 2 places to the left, dropping the percent symbol. So that's 1.08 of means multiply times 57,000. Get on your calculator and dial it up. What is 1.08 times $57,000? That will be the new salary of this employee.
Will be 6150 with 60.
61560.
Yes.
61560.
Yes.
The new salary, therefore, will be 61,560. And they also want us, ladies and gentlemen, to compute the amount of increase. We know the rate of increase is what, 8%, but they want the amount of increase. That's going to be nothing more than the old salary subtracting off, I'm sorry, that's going to be the what? The new salary subtract the what? The old salary. So the amount of increase is going to be nothing more than the 61,560 subtract off $57,000. And what does that give you for the amount of increase? Is that 4,560?
Yes, to be 4560.
4,560, correct?
Correct.
Is the amount of increase that has occurred in that salary there. Any questions how we tackled number 2? That's a percent increase problem. All right, that's how you do a classic percent increase problem, number 2. Let's see what else we got here. All right. Let's try another one. A supermarket increased the price of cheese that sold for $1.98 per pound by 3%. What is the new price of this cheese per pound? Well, for problem number 4, the new price is going to be equal to what? Is it going to be 100% plus 100 plus 3% or 100 minus 3%?
Plus.
100 plus 3%. It's an increase. So the new price is going to be 103% of the what? Of the old price, which is $1.98. And so that's how we're going to compute the new price, ladies and gentlemen. We're going to take 103% of the initial amount of that cheese, which is $1.98 per pound. Change the percent to a decimal by shifting the decimal point 2 places to the left. That means we're going to take 1.03 and multiply it by $1.98. And what do we get for the new price per pound? What do we get for the new price?
Was it $2.03?
All right, 203.
Yes.
Yeah, actually, you know, if we round off the nearest cent, the nearest hundredth, I'm getting like $2.04.
Yeah.
There you go. That would be the new price of the cheese per pound, $2.04. That represents a 3% increase from the original price. 3% increase. All right, so that problem is done, number 4. All right, let's go try another one. Number 6. A certain light beer has 20% fewer calories than the regular beer. If the regular beer has 120 calories per bottle, how many calories are in the same size bottle of the light beer? Well, ladies and gentlemen, to do number 6, the number of calories in the light beer is going to be equal to what? Is it going to be 100 plus 20% of the number of calories in the other beer, the regular beer, or 100 minus 20%?
Be minus because it says fewer.
Yeah, fewer. This is a percent decrease problem. So therefore, the number of calories in the light beer is going to be 100% minus 20% of the calories in the regular beer. So the number of calories in the light beer is going to be 100 minus 20% of the calories in the regular beer, which is 120 calories. So in other words, we're going to have to take 100 minus 20, which gives us 80%. So the number of calories in the light beer is going to be 80% of the number of calories in the regular beer, which is 120 calories. We have to take 80% of 120. Change the percent to a decimal, shift decimal point 2 places to the left, drop percent symbol. So it's going to be 0.80. And then we multiply that by 120 calories for the regular beer. And what's 0.80 times 120?
96.
Yeah, so the new light beer is going to only have 96 calories. So 96 calories is what? 20% fewer calories than 120 calories, correct? In the regular beer. That's making sense here. There's a percent decrease problem here. All right. That's a percent decrease problem. All right. Let's see. Oh, now this one here, ladies and gentlemen, is a little
I can't hear.
Mr. Ostermeyer, if you can hear us, we can't hear you.
Yeah.
Oh, I'm sorry. Let me
There
go
we go.
back.
Okay. I just wanted to make sure.
No, that's important. Thanks. Anyways, do we realize this is a percent increase problem? Because the new wage is what? Going to be greater than the old wage. So in general, our equation looks like this in general. The new wage is going to be equal to 100 plus P% increase, P% increase, which we're trying to find. So the new wage is going to be 100 plus P% of the old wage. What is the new wage? Well, the old wage is $6.50. The new wage is going to be $6.50 plus an extra 70 cents added on. 70 cents is the amount of increase. Okay. They want us to compute the percent or the rate of increase. All right. So we have the new wage is that. And ladies and gentlemen, we don't know what our percent is. Do you agree? We don't know what this guy is here. So let's just call it, you know what? Let's just call it like N or X for now, because we don't know what our, you know, what this percent has to be here. But we know the old wage is what? The old wage is $6.50. All right, so therefore, $6.50 plus a 70-cent raise is going to be really what, $7.20? That'll be the new wage. And that's going to be N% of the old wage. Now, we don't know what N is. Of means multiply. So the right side of this equation is just going to be $6.50 times N. How do I solve this equation for N? What do I divide both sides by?
650.
650. So get on your calculator and take $7.20 and divide it by 650. And you tell me what that percent N has to be here. N has to be equal to what? So what's $7.20 divided by 650? $6.50. It's going to have to be a decimal greater than 1 because the numerator is larger than the denominator. So what does it give you? 7.2 divided by 6.5. $7.2 divided by 6.5. That's going to give me 1 point. All right, 1 point. I'm going to round it off to nearest hundredths, 1.11. And so, ladies and gentlemen, as a percent, this really represents what? 111%. So what is the percent increase? What's the percent increase? It's 111% minus 100%.
11%.
Yeah, it's 11% increase, and we're done. Therefore, if a person is earning $6.50 and they get a 70-cent raise, okay, that represents an 11% increase in their wage, 11% increase. Everybody understand how we did that problem? It's 11% increase in wage. All right, it's 11% increase in wage. That was number 8. All right, let's try number 10. The enrollment in a certain elementary school was $410. The next year, the enrollment in the same school was $328. Did I say $410? I'm sorry. The enrollment in a certain elementary school is 410. The next year, the enrollment dropped to 328. Find the percent decrease in the enrollment from one year to the next. So is this a percent increase or decrease problem?
Decrease.
So therefore, we're going to say the new enrollment, we're going to set up a crude equation here. The new enrollment, okay? So this is a percent decrease problem. So we're going to start setting up our crude equation. The new enrollment is going to be 100 minus P percent of the old or the initial enrollment. But what is the new enrollment? They tell you the new enrollment is what? 328, correct? 328. And the initial or the old enrollment was 410. So 328 goes on the left side of our equation. We don't know what this percent is. We'll call it a variable n times what was the old enrollment? 410 students? Ladies and gentlemen, we have to solve this equation for n. So to do that, we divide both sides by what? By 410. So take 328 and divide it by 410. And that gives us what? 0.80? Which represents what percent? From a decimal to a percent, 2 places to the right we went. So 80%. So ladies and gentlemen, that represents really what percent decrease? That's really 80. That's really what? That's 100% minus 80%. That's a what percent decrease?
20.
That's a 20% decrease. And we're done with that problem. So it's a 20% decrease in enrollment. So the enrollment goes from 410 drops to 328. That represents a 20% decrease in enrollment. What would be a 100% decrease in enrollment from 410? 100% decrease would mean you'd have how many new students? I mean, how many students after the decrease? It'd be what? 100% of 410 is 410, correct? That means if you had a 100% decrease from 410, you would have what? 0 students, correct? You lost everybody. That's not good. All right. So that's how we work, ladies and gentlemen, on percent increase or decrease problems. Now I want to show you a couple of discount problems. So we're going to go shopping here. Number 14. It says, on opening day, a new music store offers a 12% discount on all electric guitars. If the regular price on a guitar is $550, what is the sale price on that guitar? Okay, so this involves, okay, hold on. And so, ladies and gentlemen, we're going to try to figure out the, the sale price here on the guitar. Now, I have a question for you. Is the sale price going to be more or less than the original price of the guitar?
Less.
Less. So this 12%, does it represent a percent increase or decrease from the original price? What do you think?
Decrease.
Yeah, it's a 12% off sale. Do you agree? That means 12% decrease. In other words, the new price is going to be what? Represent a 12% decrease from the original price. So this is kind of like a percent decrease problem, is it not? Computing this new price? All right. So we can turn it into a percent decrease problem. So the new price, by the way, the new price has a name. It's called the what? Sale price. Do you agree?
Right.
So the sale price of this guitar, the new price, ladies and gentlemen, is going to be what? A 12% decrease from the original price. So the sale price is only going to be 100 what? Minus 12%. of the what? The original price. Isn't that true? So the sale price is really going to be 100 minus 12 is what? 88. So it's going to be, the sale price is going to be 88% of the original price, which was what? What was the original price of that guitar? Was it 500 or 550? I forgot. Was it 500 bucks or 550? 550.
550, yes.
Okay, 550. So get on your calculator. How do you take 88% of 550? Change a percent to a decimal, drop the percent symbol. So this is right, 0.88 times 550, and you'll have the new sale price. Go ahead and do that. What's 0.88 times 550 bucks? That represents our sale price. So 0.88 times 550, ladies and gentlemen.
484.
484. So the sale price is going to be $484. So how much are we saving? What would be the amount of discount that we're saving? Well, that would be the original price, which is 550 bucks minus the new sale price. This would be the amount of money that's taken off. The rate at which the price is decreased is 12%, but the amount that is taken off is 550 minus 484. And so the discount is $66. So we save 66 bucks. So ladies and gentlemen, $66 is the discount. The discount rate is 12%. Let me write that down. That's important. So when I say discount, that's a dollar figure. That's $66 off. But if I say discount rate, remember a percent's a rate. So if I say discount rate, that's what? 12% off, correct? Is that true? Okay. So the new price, the sale price will be 66 bucks. That's a classic discount problem there. We all shop for discounts. I know I always try to find a discount here. Okay, here's a good one. A bedroom a set normally sells for $1,450 is on sale for 10% off. If the sales tax rate is 5%, what is the total price of the bedroom set if it is bought while on sale? Well, ladies and gentlemen, the first thing we need to find out is what the sale price is. Do you agree? So let's write down on our paper for number 16, sale price. The sale price is the new price. And it's going to be what? Is it going to be 100 plus 10% of the original price or 100 minus 10% of the original price? What do you think the sale price is going to be? Well, the sale price better be what? Less than the original price. Do you agree?
Correct.
So therefore, the sale price should be 100 what? Not 10% of the original price, but 100 what? Minus 10%. Do you agree? Of the original price. So we're going from the original price to the new price, ladies and gentlemen. This is a 10% decrease problem, is what it really is. It's a percent decrease problem. So the sale price is going to be really 100 minus 10% of the original price, which is $1,450, $1,450. We can now find the sale price. The sale price really is going to be 90%, therefore, of the original price of $1,450. Change the percent to a decimal, shift decimal point 2 places to the left, 0.90, and then we multiply by the 1,450 bucks. And you tell me, what is my sale price going to be? Well, it's going to be that 0.9 times 1,450.
1305.
There you go. So the sale price is going to be $1,305, correct? But, ladies and gentlemen, we also have a what? 5% what? Sales tax. Isn't that true? Now, is this sales tax going to be added on or subtracted off from our sale price? Is this 5% sales tax going to be added on or taken away from our sale price before we go up to the register? It's going to be taken. It's going to be what? That's sales tax. So are we gonna have to add that on to our sale price or take it off? Sales tax is always what? Added on. So we're gonna add it on to the sale price. Of $1,305. And so, ladies and gentlemen, what price do we pay at the register? Price we pay is going to be equal to what? The price we pay at the register, is it going to be 100 plus 5% of the sale price or 100 minus 5% of the sale price? Is the sale price added on or taken off from the sale price?
Added.
It's added on. So the price we pay at the register is going to be 100 plus 5% of the sale price. Because in going from the sale price to paying at the register, ladies and gentlemen, we've experienced a 5% increase in the price because we got a 5% increase due to sales tax. So therefore, the price we pay at the register is going to be 105% of the sale price. And the sale price is $1,305. So how do you take 105% of 1305, change the percent to a decimal, shift the decimal point 2 places to the left, drop the percent symbol, and then we multiply. What's 1.05 times 1305? Because that's the amount of money we're going to be paying at the register. I'm getting $1,370.25, correct? That, ladies and gentlemen, is what we owe at the cash register. That includes the what? The sale price after there was a 10% discount. And after the 5% sales tax was added on to the sale price. That's what we're going to owe. So this problem has two main steps. First, you have to find the sale price by entertaining a percent decrease problem. Then, ladies and gentlemen, you have to entertain a percent increase problem and then adding 5% sales tax onto your sales price to get the final price you pay at the register. Two main steps. Everybody see how we tackle that problem? Two main steps. First, compute sale price, then add 5% onto it, and you'll get your total price at the register. All right, classwork number 1 has arrived, ladies and gentlemen. I would like you to try a couple of problems here. Let's see here if we can dredge up a couple. Go back up here. All right, we can call this classwork number 1 here. Ladies and gentlemen, we don't have a, let's see, we don't have a ton of time. But I'm going to have you do problem number 15. Everybody see that there? A man buys a washing machine that is on sale. The washing machine usually sells for $450, but is on sale for 20% off. If the sales tax rate is 6%, how much is the total bill of the washer machine when you go to the cash register and pay? Try number 15, classwork number 1.
All right. $90. 36. So it's 2160. Six. Okay. Next. Oh, I hate this.
Anybody need more time on this problem? Anybody feel confident? How much are we going to pay at the cash register?
$381.60.
$381.60. Anybody else get that?
Yes.
Yes.
There it is, ladies and gentlemen. The problem really is going to have to be worked in two major steps. First, you have to compute the sale price, okay, of the washer. And there's a 20% off sale. So that means the sale price is only going to be 80% of the original price, meaning $360.
Oh, okay. Okay.
Correct? Because there's a 20% off sale. So this is a percent decrease problem you have to entertain first. You see that? Now that you know the sale price, you're going to have to entertain a percent increase problem because we have to what? Add on 6% sales tax. So now the final price we pay at the register is going to be equal to 100 plus 6% of the sale price, which means at the register we pay 106% of $360, which means at the register we're going to pay 1.06 times 360 or $381.60. And we're done with that problem. Two main steps, correct? All right. If you did not get that problem correctly, please do, make a mental note or actually make corrections on your paper there, because we want to turn this into a learning experience, okay? That's what it's all about, is to try to learn from our mistakes here, okay? All right, so that section there dealt with percent increase or percent what? Decrease problems, and also discount problems, which inevitably did get us into percent decrease or increases again, all right? So any questions about further questions on that section there? 6.5? If not, we can close the book on that one and move on to 6.6. Okay. All right, let's go on inward on to section 6.6 in our textbook and see what it's all about. Oh, it says interest. All right. Does anybody know what interest is? Interest. In the business world, what's interest? You're looking at it. What's this person holding in their hands?
Money.
Money. Interest is money, ladies and gentlemen. Now, interest can be a good thing or it can be a bad thing. Interest is a bad thing when you're paying like on a student loan. You have to pay interest back to the bank for borrowing the money. Or if you take out a mortgage for a home or a boat or a car, you have to pay back not only the original amount that you borrowed, but you have to pay back something called interest. The bank wants to make money for having lended you the money. Do you agree? That's a bad thing when we got to pay interest, ladies and gentlemen, on loans. When's interest a good thing? When can interest work for us? Well, that would occur if we have maybe some money where we can invest our money, maybe like in the stock market or maybe a mutual fund or like a certificate of deposit. Do you agree? Then our money can earn us money over time, can it? Okay, that's when interest is a good thing. All right. So we're going to, start working with a couple of interest problems here in section 6.6. And I'm just going to go right on down to the exercise set here, ladies and gentlemen. And before we actually dive into some problems, I need to show you the formula that we're going to use to compute what is called simple interest. And what is simple interest in section 6.6? Well, the definition of simple interest is the amount of money, okay, computed from only the principal. That's what simple interest is, ladies and gentlemen. What's this thing called principal here? Principal is the initial amount. It's the initial amount of money that is involved in a situation. Now, let me give you an example. For instance, if you go down to the local bank and you deposit $5,000 into a certificate of deposit because you want to have, you want your money to earn you some interest. That's called investing your money, ladies and gentlemen. Well, the principal is called $5,000. That's the initial lump sum of money you put down into the account. If you go out and take out a loan, let's say for $10,000 to buy a car, wow, am I outdated? That might have been the case back in 1980. Do you agree? Yeah. Unfortunately, cars are just their prices are brand new cars are astronomical in price. Let's say you go out and take out a loan for what, $30,000 to buy a brand new vehicle. Well, ladies and gentlemen, the initial amount of money you take out from the bank, that $30,000, that's called the principal. That's the initial amount of money that you, bare minimum, are going to have to pay back to the bank.
Yes.
But you and I both know that the bank wants something above and beyond that. Do you agree? They want something called what? Interest too, don't they? Okay. All right. So the principal is the initial amount of money that is involved in either depositing money or taking it out, like in the form of a loan or like a credit card or, a mortgage or something. All right. Okay. So how do we compute simple interest? Well, there's a formula. This is called the simple interest formula that is used in the business world, and I'll bet dollars to donuts is being used as I speak to compute interest somewhere around the world. Simple interest formula, and this is it. I is equal to P times R times T. That's called the simple interest formula. That is how simple interest is computed by using this formula, where I equals, what do you think I represents?
Interest.
That's the interest. And of course, we know interest to be a what? A dollar figure, correct? That's what interest is. Interest is money. P is, what do you think P stands for?
I want to say percent price.
Well, no, that would be the principal.
Yeah.
That's the initial what? The initial amount of money that's involved in, either depositing, opening up an account, depositing money, or taking out a loan of some sort. R is called the almighty interest. What do you think?
Rate.
Yeah, the almighty interest rate. And ladies and gentlemen, the interest rate initially comes at us in the form of a percent, but we always have to convert it into a what before we incorporate it into the formula?
Decimal.
Must convert it into a decimal. That's very important. So just kind of keep that in mind. Now, T stands for almighty something we can never get back, and it's called what?
Time.
Time. And in this formula, ladies and gentlemen, time is always to be in years. Time is always to be in years. So like if we pay on a loan over the course of 5 months, or excuse me, let's say 60 months, we have to convert 60 months into years. If we pay off a loan over the course of 190 days, we have to convert 190 days into a fraction of a year. Okay. That's called a simple interest formula there. And that's going to enable us to compute simple interest. Let me know when you got that down and we can begin to go back to our book and start doing a couple problems here. All right. Notice the interest we're going to pay, ladies and gentlemen, is directly proportional to what? The amount we take out for a loan. Also the interest rate. The higher the interest rate, the more interest we're going to be paying back. And if you pay off the loan over a longer period of time, do you agree? You're going to be paying back the financial institution more money in interest, aren't you? Okay.
Mm-hmm.
So all three of these figures here add up to our demise if we take out a loan. Do you agree? The larger all three of these figures are, that means the more interest the bank's going to get out of us. This is a good thing if you invest your money, though. It's wise to invest your money at a high interest rate, isn't it? For a long period of time. You'll earn a lot of money on your money. Okay. That's called investing money. That's where you make your money work for you. All right, let's go back to our textbook and see if we can dig into a couple of these here. All right. Number 2, how much simple interest is earned on $5,000 if it is invested for 1 year at 5%? So we're going to do problem number 2 here. Ladies and gentlemen, we want to compute the amount of interest that is going to be accrued over the course of 1 year. What is our principal P? What's the initial amount of money?
The initial amount.
Initial amount of money we invest is what?
5,000.
$5,000 is your principal. Yeah. What's the interest rate R? Number 2, 5%. But of course, 5% must be turned into a decimal. So what would that be?
0.5.
Not 0.5, 0. What? 0.5, correct?
0. Yes.
Okay. And what amount of time we leaving the money in the account? What's T?
1 year.
1 year. Okay. We are able now to compute the amount of interest that we're going to earn if we invest our money at this rate for 1 year. The amount of interest we will earn is equal to principal multiplied by the rate times the time. So the amount of interest we will earn is the principal, which is $5,000, times the interest rate, which 5% is 0.05, times 1 year. Get on your calculator, ladies and gentlemen, dial it up. How much interest are we going to earn there?
$250.
Yeah, $250 is the amount of interest that we earn over the course of 1 year. That's cool. Isn't that neat? Just for leaving your money sitting in that account for 1 year, ladies and gentlemen, without touching it, just going away for 1 year, coming back at the end of the year, you will have earned $250. Isn't that amazing? Your money actually went to work for you. So what would be the new amount in your account after 1 year? Well, it's going to be your principal plus your what? Interest earned. You're now going to have $750. Isn't that cool? Your interest earned you money. That's a neat thing, huh? The trick is to try to invest at a what, high interest rate. Do you agree? Invest your money at a high interest rate so you get a good return. And lucky is the person that finds that high interest rate or locks into one. All right, we all done with that one there? That's just a very basic, simple interest problem, number 2 in section 6.6. Let's see. All right, we could try another one here. Number 4, a local bank pays 5.5% interest, annual interest, on all savings account. If $600 is invested in this type of account, how much will be in the account at the end of 1 year? Well, first we have to compute the amount of interest we're going to earn over the course of that 1 year. So to compute the amount of interest we're going to earn, interest is equal to principal times rate times time. The principal is equal to what? What's my principal there for number 4?
Be $600.
Yep, $600 we plunked into a savings account. And what's the interest rate? Are
5.5.
5.5%. Change that to a decimal. What's 5.5% as a decimal? Shift the decimal point 2 places to the left. 0.055.
Yes.
And how long are we leaving that money in the account?
1 year.
1 year. And that's all there is to this problem here. All we have to do is compute the amount of interest earned. It's going to be the principal, which is $600, times the interest rate as a decimal, 0.055, times the time, which is 1 year. Get on your calculator and tell me the amount of interest that we will have earned.
$33.
$33. So at the end of 1 year, the account balance is going to be equal to our principal, which was $600, plus an extra $33. So we will have earned $33 over the course of 1 year. Now, you know, some people would argue, well, you could maybe find more in bottles and cans along the road in 1 year than $33. Do you agree?
Mhm.
But granted, ladies and gentlemen, I mean, you are earning $33 just by leaving that amount of money in your account. And, you know, hey, it's better than paying $33. Could be worse. Make sense there? Simple interest so far. You get it? No pun intended. Makes sense there? Sense? Money? Oh. All right, that was a bad joke. That was a real bad joke. Now, all right, let's see. All right. If we, all right, that's just another typical one here. Here we go. Let's show you one like number 10. It says, if a loan of $1,200 at 9% is paid off in 90 days, ladies and gentlemen, what amount of interest would we have to pay back to the bank? If we take out a loan from a bank, an amount of $1,200, and it's 9% simple interest rate, if we pay that loan off in 90 days, how much interest would we have to pay back to the bank in addition to that $1,200? Well, we're going to find out. All right. Now, so problem number 10 here. Notice we're talking days now, correct? We're talking days. What would be my principal, the amount I borrowed?
1,200.
1,200, and the interest rate R would be?
9%, but if you move it this
So what would that be as a decimal? 9%.
0.09.
0.09. What amount of time? What amount of time are we paying off this loan?
90 days.
But ladies and gentlemen, time cannot be in days. It must be in years for the simple interest formula. So now look at, here's the kicker. I've noticed in your textbook, and this is something they used to do in the old days before we had computers. They would call a year, ladies and gentlemen, back in the old days, not 365 days, because that's too difficult for the calculations. You know what they would use in the old days for a year before calculators? They would call it 360 days because it eased the burden of calculations. Yeah, 360 days. That's the way they used to do it in the old days for calculators, the financial institutions. They call 1 year 360 days. So we're paying this loan off over the course of 90 days. So the time in years would be 90 divided by 360th of a year. That's the number of years we're paying this loan off over, because we're paying it off over 90 days. So 90 days really represents 90 360th of a year. And do you agree this reduces down to what, 1/4 of a year?
Mhm.
Do you agree it's a lot easier to reduce 90 over 360 as opposed to 90 over 365? You see, that's why in the old days, they used 360 for the number of days in a year, because it made the calculations easier. And so, ladies and gentlemen, here we go. The amount of interest that's going to accrue over that 90-day period is going to be equal to the principal, which is $1,200, times the interest rate, which is 0.09, times the time, which is what, 1/4. Can you get on your calculator and dial this up, multiply all these numbers together? We can work with fractions on our TI-34 or TI-30, correct? That's no big issue. Okay, get on your calculator and tell me how much interest we're going to owe.
27.
What was it, 27?
Yes.
Yeah.
We're going to owe $27. And so what is the total amount we're going to pay back? Total amount paid back. Well, that's going to be the principal, plus it's going to be what? The interest. The principal is the $1,200 we have to pay back, plus we owe an extra $27 of interest. Hence, when all is said and done, we will have paid the bank back $1,227. Correct? Simple interest problem. So that's how simple interest basically works. Simple interest is basically interest that's computed only on the principal alone. But ladies and gentlemen, there is another type of interest out there. It's called compound interest. Have you ever heard of that before? Compound interest?
I think I have.
Yeah, that's in all reality, the interest that's really used in financial institutions is called compound interest. How does compound interest differ from simple interest? Well, let me define for you what compound interest is. All right, what is compound interest? Well, we know simple interest is, just interest computed on principal only, so it's just money. But compound interest is a little bit more complicated. Compound interest is computed on not only the principal, it's computed on the principal like simple interest is computed on the principal, but later on it's also computed on interest that's already earned or accrued. So compound interest is a little bit more complicated. It's money computed on the principal of like a loan or the amount you deposit, and also it's computed on the interest that has already accumulated. Okay, that's compound interest. So compound interest is kind of the analogy I like to use for compound interest is, suppose we have a hill of snow, and at the top of the hill of snow, we make a small snowball, ladies and gentlemen. And then we let that snowball start to roll down the hill that's covered with snow. Do you agree as the snowball rolls down the hill a little bit, it's going to pick up more snow and become what, bigger?
Mhm.
But, but if the snowball becomes bigger, ladies and gentlemen, that means it's going to become heavier, which means it's going to push it deeper into the snow, in which case it'll pick up even more snow. Do you agree? Because it's heavier. So it's going to grow even at a faster rate. Do you agree? Which means it's going to become even heavier, forcing it down deeper into the snow, picking up more snow and growing at an even faster rate. That's the marvel, ladies and gentlemen, of compound interest. It grows very quickly compared to simple interest. Pretty amazing, isn't it? Okay. Let's see if we can show you an example of computing compound interest. Okay. All right, ladies and gentlemen, we're going to try number 14 here. It says A savings account pays 5% compounded annually, pays 5% interest that is compounded annually. If $10,000 is deposited in the account, how much is in the account at the end of 2 years? Okay, look at, if this was just simple interest, ladies and gentlemen, problem number 14 would be pretty simple. Do you agree? It would be nothing more than what? The amount of interest earned, if it was simple interest, would be equal to the principal, which is $10,000, times the interest rate, which is what? Was it 5%?
Yes, it was.
Times 2 years. Do you agree? That would be the amount of interest you earn over 2 years if it was simple interest. But that's not the way compound interest works. You see, simple interest is only computed from the principal alone. But compound interest is a little bit more complicated. It's money or interest computed on principal and interest that's already accumulating from previous time periods, okay? So we're gonna work this problem out. We're gonna try to figure out how much money is gonna be in our account if we initially put down what? $10,000 at an interest rate that is what? 5%. And the total time is going to be 2 years. But the interest, they tell us, is compounded annually. What does it mean to say interest is compounded annually? That means, ladies and gentlemen, the bank will pay, the bank computes interest, I'll just say computes interest, once per what? Once per year. The bank actually computes the interest once per year. That's what it means to say that the interest is compounded annually. Annual means one time per year. Yearly, okay? All right, so how are we going to figure out how much money will be in this account at the end of 2 years if we invest $10,000 at 5% interest compounded annually, and we leave the money in the account for a total of 2 years? Well, here's how we do it. We got to do it kind of like in steps. So we're going to call this year number 1. On your paper, put year 1. All right, year number 1. How much money do I put in my account during the first year, the initial investment? What's my principal? $10,000 goes into the account, correct? Year number 1. All right, ladies and gentlemen, now how much interest do I earn over the course of 1 year? Well, interest is equal to principal times rate times time. So that means over the course of the first year, I earn, here's my principal, $10,000, times the interest rate, which is what? 0.05. And how much time does the interest have to accrue for the first year? 1 year, isn't that true? 1 year. Okay, get on your calculator and dial this up. Do you agree that that will what? Earn us $500 in the first year of interest? Did I do that calculation correctly? I believe so. 1, 2, 3, 4.
Yeah, you did.
Okay, so ladies and gentlemen, now what would be the balance or the new principal? What would be the balance or the new principal at the end of year 1? What's going to be in our account at the end of year 1? The new principal, ladies and gentlemen, I like to call P prime. Prime means it's an updated value of your principal. It's new. It's not the same as P, the original principal. What's our new principal? It's going to be the old principal plus the interest that was accrued or earned during the first year. So it's going to be the $10,000, our old principal, plus what? $500 of interest that's earned during the first year. So our new balance or principal is going to be $10,500. That's our new balance or new principal. But ladies and gentlemen, we're leaving our money in this account for how many years?
2 years.
2 years. So now we got to venture into year number 2. So on your paper now, I want you to write down year 2. But what's our new principal? Our new principal has been updated by $500. Now the new principal is $10,500. How much interest are we going to earn during the second year with our new principal now? Well, the amount of interest we'll earn during our second year is going to be our new principal, which is $10,500, times the interest rate of 5%. That doesn't change, times 1 year. So what amount of interest do we earn during year 2? Go on, get on your calculator and dial that up now. I'll bet when we get done that this new interest earned during the second year is going to be greater than the amount of interest earned in the first year. You're looking at the magic of compound interest. What is it?
525.
Aha. So in year number 2, we earn an extra, what, $25 worth of interest, don't we? Why do you think the interest earned in year 2 is higher than that earned in year 1, ladies and gentlemen? What has changed? Well, I'll tell you what's changed. In year 1, we've earned $500 of interest, which upped our what? Principal from $10,000 up to $10,500. Now we're going to earn more interest in the second year because our principal is larger now. Do you agree?
Mm-hmm.
Now, what's going to be our new balance at the end of year 2? The balance at the end of year 2. Well, that's going to be our starting balance at the beginning of year 2, which is what? What was our starting balance at the beginning of year 2? Not $10,000. No, it's what? It was the $10,500. Plus, how much more interest did we earn during the year 2? $525. How much money is going to be in our account after 2 years now? Just add these together, and what do we get? We get, what is it? 11025. Is that correct? $11,025. I think I did that correctly. That looks good. Okay. Is that right?
Yes, it's correct.
So, ladies and gentlemen, you see how this is working here? You see, compound interest is amazing because the amount of interest that we compute in year 2, okay, is compounded on the fact that we earned $500 of interest in the first year added on to our interest, our principal. So compound interest is interest that's computed not only on the principal, but interest that's also earned already. So you can see the interest starts to increase every year we leave our money in the account because the interest is compounded. It's not simple interest. Now, if we did this problem with simple interest, ladies and gentlemen, get on your calculator and dial this up. Just multiply all these together. Tell me how much money we would have in our account or how much interest we would add on if we leave the money in the account for 2 years with simple interest only. Multiply all this together. What do you get here?
1,000.
What is it? 1,000?
Yes.
$1,000. Okay. So what would be the balance after 2 years if we just had simple interest computed, ladies and gentlemen? Well, that would be $10,000, the principal plus $1,000. In other words, we would only have $1,100 in our account. Do you agree? $1,100, no, $11,000, excuse me. We'd have $11,000 in our account after 2 years if our interest was computed as simple interest. But look at, because it was computed as compound interest, we've earned an extra what? How many dollars? $25. Do you agree?
Mm-hmm.
You see that there? So compound interest pays more than simple interest, ladies and gentlemen. Compound interest pays more because it grows faster. It's like the snowball that picks up more snow, gets heavier, picks up even more snow, therefore it grows even bigger because it's now even heavier, picks up even more snow and grows even bigger at a faster rate. Do you agree? That's what's happening with compound interest. So hopefully you can appreciate the difference between simple and compound interest. Compound interest grows quicker than simple interest. Gives you more money. Always try to invest your money at compound interest as opposed to simple interest. All right. Let's see here, 148. Son of a gun, we're running shy of time here. Okay. I can try another compound interest problem with you, ladies and gentlemen. Number 15, it says if $8,000 is invested in a savings account that pays 5% compounded quarterly interest, how much is in the account at the end of the year? Well, when interest is compounded quarterly, that means that the bank pays into your account not one time per year, but how many times per year? 4 times per year.
Four times?
Yeah. The way it works is this, ladies and gentlemen. If interest is compounded annually, the number of payments is going to be 1 time per what? Per year. If your interest is compounded semi-annually, interest is paid 2 times per year. If the interest is compounded quarterly, there's 4 payments per year into your account. If the interest is compounded monthly, then there would be what? 12 payments per year in your account. Do you agree? See how that works there? All right. Number 15, the interest is compounded what? Quarterly. So what we're going to do here, as long as we initially have a principal of $8,000, and the interest rate is 5%, which is 0.05 as a decimal. They want to know how much money we're going to have in the account at the end of the year if the interest is compounded quarterly. So here's what you do on your paper. You put, how many quarters are there in a year?
4.
4. That's why there's going to be 4 payments per year or 4 computations per year to compute this interest. So we need to write down on our paper the first quarter of the year. The first quarter of the year, ladies and gentlemen, is called the first 3 months. The first 3 months of the year. How much interest is going to be computed in the first quarter? Well, interest is equal to our principal, which starts out at $8,000, times the interest rate, which is 0.05, times what fraction of a year, ladies and gentlemen? If I leave this money in the account for just 1 quarter, the first quarter of the year, which is 3 months, that's what, 1/4 of the year?
Mhm.
Can you get on your calculator and dial this up to me? Tell me what amount of interest we earn or accrue during the first quarter of the first year. It lies in that product there. Multiply all those together and tell me what you get.
$100.
All right, $100. Now, what's going to be the new principal? Well, the new principal, as I'll call P prime, is going to be the old principal, which is $8,000 plus $100. So the new principal is going to be $8,100. Now we carry this over into the second quarter of the year. The second quarter is the second 3-month period of the year. What amount of interest will accrue during the second quarter? Well, what's the new principal? $8,100 times the interest rate of 0.05 times another 1 quarter a year. Get on your calculator, dial that up. How much interest is accrued or computed during the second quarter of the year? Tell me what that multiplies together to give us. It will be greater than $100, guaranteed. Tell me what you get.
$101.25.
All right, $101. So what's going to be the new principal at the end of the second quarter? Well, that's going to be the starting principal, which was what, $8,100 plus an extra $101. And that nets us what? 8,201?
Mhm.
$8,201. And now, ladies and gentlemen, we have to carry this into what? Quarter number 3, third quarter of the year. This is the third 3-month period of the year. So we're going to try to figure out what's the new principal at the end of what? 9 months, do you agree?
Mm-hmm.
What's our amount of interest computed in the third quarter? Well, what's our new principal? It's 8201. That gets multiplied by the interest rate, 0.05 times again, 1/4 of the year. Get on your calculator, dial it up, tell me how much interest is computed during the third quarter. Thank goodness we're almost done with this problem. It's got to be more than 101.
Be 102.
$102. All right, so therefore the new principal is going to be what? At the end of the third quarter, the new principal is going to be the old principal, which is 8201 plus $102, which is now going to be 8303, right? Finally, ladies and gentlemen, the fourth quarter. Thank goodness this is only for 1 year. Could you imagine if we invested this for 20 years? We would have 80 calculations to do, 80 of them. Thank goodness this is 1 year. All right, during the fourth quarter, what amount of interest is going to be computed? Well, we take the new principal, which is 8303, multiply it by 0.05 times 1/4 more. Get on your calculator and tell me, ladies and gentlemen, how much interest is computed finally for the fourth quarter of the year. And it will be and should be larger than 102. Notice the interest.
103.
$103.
Mm-hmm.
Finally, what's going to be the final balance in our account at the end of 1 year? At the end of the fourth quarter is at the end of 1 year. At end of 1 year, we would have how much in our account? Well, the old principal is 8303 plus $103 more. That's going to be what, 8406? That, ladies and gentlemen, is the amount of money you'll have in your account at the end of 1 year if your interest is compounded quarterly at 5%. Agree?
Mm-hmm.
All right. Do we understand how to compute just simple interest versus compound interest, ladies and gentlemen? I've shown you enough examples, I think, whereby we're going to be good on that. All right, we got to move on. Unfortunately, I don't have a classwork for this section. If I have time to roll it into the last classwork, if we even have a last classwork, I will do so. Okay, but I really want to get into the next section. We good on simple and compound interest, ladies and gentlemen?
Mm-hmm.
All right, let's get into the last section today, which is section 7.1, starting a new chapter. It's entitled Measurement. In section 7.1 is unit analysis, where we're going to deal with length units of measurement, ladies and gentlemen. Length units of measurement. Okay. And I'm just going to scroll all the way down to our problem set here. All right. So we're going to look at units of measurement in section 7.1. Can anybody give me typical units of measurement we use in our everyday lives? Inches.
Inches and feet.
Feet. Yards. Miles. Do you agree? Are all typical units of what measurement. As far as length is concerned, we're only going to consider length today, not volume or weight. Okay, these are typical English units, ladies and gentlemen. We need what are called unit conversion factors. Unit conversion factors are unit rates. They're unit rates. And I'm going to show you a couple here, ladies and gentlemen. Here's one unit conversion factor. There's 12 what? 12 inches per how many feet? 1 foot? That's called a unit conversion factor. That relates inches to feet. 12 inches per 1 foot. That's a unit rate. Isn't this also a unit rate we talked about in the past? Remember, when a rate has a denominator of 1, it's called a unit rate. Ladies and gentlemen, there's 5,280 feet per every 1 mile. That's a unit conversion factor. There's 3 feet per every 1 yard. That's a unit conversion factor. You see that there? These are called unit conversion factors. They're going to enable us to convert from one unit to another unit within our measuring system in this country. Okay. All right, let's see if we can do a couple conversions now using some of these unit conversion factors. Let's go back to the textbook. Let's try a couple of these out here. Ladies and gentlemen, suppose I want to do problem number 1 here, where I want to convert 5 feet to so many inches. 5 feet to inches. I'm going to show you what's called the unit analysis way, ladies and gentlemen, of unit, or excuse me, it's called dimensional analysis way of doing unit conversions here. We want to go from feet to inches, correct? So here's how we do it. We put 5 feet down on our paper, and you can put it over 1. We're going to have to multiply this 5 feet by what's called a unit conversion factor that will take us from feet and take us to what units? Inches. Do you agree? We want to go from feet to inches. So I want to get rid of feet, ladies and gentlemen. I want to go to inches. Because of that, my unit conversion factor is going to have feet in the denominator and inches in the numerator. Because look at, when I multiply these together, my feet units will cross cancel out. And I'll go from feet to inches. Everybody see that there? Now, what conversion factor am I going to use above to take care of this?
The first one.
Yeah, we will put 12 inches over 1 foot, correct? That'll take care of this business here. So now what we're going to do is we're going to multiply these fractions together, 5 times 12, and we're going to place that over what? 1 times 1. And now what would our units be? Feet are gone. They cross canceled out. We're left with what? Inches. What's 5 times 12? Ladies and gentlemen, we're done.
60.
We have discovered that 5 feet is equal to 60 inches. That's how you formally convert. It's called dimensional analysis, the method I just showed you for converting here. Let's try another one, okay? Any questions about that one there? All right. Suppose we want to go backwards. We want to convert 10 feet to inches. Number 3, 10 feet is equal to how many inches? So we want to go from 10 feet back to what? So many inches. So how are we going to accomplish that? Well, I'm going to put down the 10 feet on my paper and put that over 1. And then I'm going to have to multiply this, ladies and gentlemen, by what conversion factor? I want to get rid of what? Feet. Wait a minute, do I have that right? It was 10 feet to inches, or was it 10 inches to, yeah, oh no, okay, I'm good. All right, so I multiplied by my same conversion factor, that is 12 inches per what? 1 foot?
Mm-hmm.
Now by multiplying these fractions together, notice the units of feet cross cancel out or reduce out, leaving me with inches. And I'm going to have 10 times 12 over, technically, 1 times 1 inches, which means I'm going to have 120 inches. And we're done. So there you go. 10 feet is 120 inches. Can we go backwards, do you think? Do you think we should be able to convert from inches back to feet?
Mm-hmm.
Should be able to. I'm going to give us an example. If, ladies and gentlemen, if I have 360 inches, then I want to convert this back into so many feet. How do we do this? Well, we put 360 inches down on our paper, place it over 1. Now we're going to multiply this by a conversion factor that will enable us to get rid of our inches and go to feet. Because I want to get rid of inches, I got to make sure my inch units cross cancel out. So I have to have inches down here for favor of going to feet in the numerator. Now the conversion factor we're going to use is what? 1 foot is to what? 12 inches? Do you agree?
Mm-hmm.
Everybody see how I set that up there? Now let's multiply these together and notice the inch units cancel out, leaving us with 360 times 1, which is 360. And that's divided by 1 times 12 or 12. And that will take me to feet. Now get on your calculator. What's 360 divided by 12? And you got your answer. What's 360 divided by 12?
30.
Done. So they're done in 360 inches is 30 feet. Everybody understand how I'm multiplying by these unit conversion factors to take care of the conversion. Notice how we always want the units that we want to get rid of, we want them to cross cancel out. And we want the units we want to go to in the numerator. Notice that. All right, let's try another one here. Let's see. How about 9.5 yards to inches? We'll do number 8. 9.5 yards, we want to convert into what? So many inches. But Houston, we have a problem. And the problem is this, ladies and gentlemen, I don't have a direct unit conversion factor that links together yards and inches, do I? All I've shown you is unit conversion factors that link inches and feet, feet and miles, and feet and yards, haven't I? So here's what we may have to do, and this happens all the time. Sometimes we may have to multiply by more than one unit conversion factor to finally get to our destination. So far, we've only had to multiply by one of them, correct, to convert. But here, ladies and gentlemen, we're going to have to multiply by more than one. In fact, here's my game plan. I want to go from yards to feet first, and then from feet to what? Inches. Everybody see that there? That's what I'm going to do. I'm going to go from yards to feet and then feet to inches. I'm going to have to take it in 2 stages here. So therefore, I put on my paper 9.5 yards, and I place this over 1. First of all, I'm going to go from yards to feet. Well, what conversion factor do I use that relates yards and feet? Oh, here we go. 3 feet is to 1 yard. Do you agree? We got to use this unit conversion factor there. So therefore, I'm going to have to multiply this by, now I want to get rid of yards and I want to go to feet. So I got to have yards in the denominator so that the yard units cross cancel out and take me to feet. We know 1 yard is what? 3 feet. Everybody see this first unit conversion factor, how I arranged it? It has to be this order because we want yards to cancel. But ladies and gentlemen, I don't want to stop at feet. I want to now go from feet to inches. So I multiply by yet another conversion factor that will get rid of feet and take me finally to inches. So now when I multiply this fraction right here by this fraction, the feet units cross cancel out. So look what's going on here. The yard units cross cancel out, the feet units cross cancel out, and I'm left with inches. That's what I want. So what conversion factor do I put here? Where do I put the 12 and the 1? Does it matter? Oh, it matters. What was it, ladies and gentlemen? 12 inches was to what? 1 foot. Do you agree? So where do I put the 12? Top or bottom?
Top.
Top. And the 1 foot goes down there. There we go. Now let's actually multiply everything together. In the numerator, we have 9.5 times 3 times 12. And that all sits over my denominator of 1 times 1 times 1. And the units will be what? Inches. Get on your calculator and dial this up. What's 9.5 times 3 times 12? You got your answer. Go ahead and do that. What does that give you?
342.
342. So therefore, 9.5 yards is 342 inches, and we are done. See how we strung together 2 unit conversion factors here? We had to, because we did not have a unit conversion factor that linked directly yards to inches. If we had one, I would have used it. You may have to do that. You may have to string together many unit conversion factors to finally go to where you need to go. So that happens all the time. All right, let's see here. All right, let's try maybe another one. Number 12 here. We want to convert 6.75 miles to feet. So 6.75 miles. We want to convert that to feet. All right, so what conversion factor am I going to use, ladies and gentlemen, to go from miles to feet? Miles to feet.
Oh, the middle one.
The middle one right here, because this relates feet and miles. Okay, so therefore, I'm going to multiply it by my unit conversion factor where I have miles in the denominator. So the miles cross cancel out, and I want to go to feet. Now, it's a well-known fact that 1 mile is 5,280 feet. This will take care of it. So now we multiply our numerators across, which is 6.75 times 5280. Technically, this is going to be divided by 1 times 1 or 1, and my units that survive will be feet because the mile units cross canceled out. Get on your calculator and dial it up. Tell me how many feet is in 6 3/4 mile.
$35,640.
Thank you. 35,640 feet would be in 6.75 miles. So 6.75 miles, as it turns out, is 35,640 feet. So if you get on your treadmill and walk 6.75 miles, ladies and gentlemen, you will have walked 35,640 feet. Isn't that amazing? That's a lot of feet. So I showed you how to do conversions with length units in the English system of measurements, or sometimes they call it the US system of measurements. Because in reality, ladies and gentlemen, do you think the whole world uses the same units we use in this country for measurement, for length? No. In like Canada, they use the metric system of units for length. In Canada, ladies and gentlemen, they're using metric units of length. And can anybody give me a metric unit of length that they use up in Canada or over in Europe or South America? Because most of the rest of the world uses the metric system. They don't use our system. Can anybody give me a unit of length in the metric system?
Kilometers.
Kilometers, yeah. Kilometer or kilometer. The debate is still out how to pronounce it. And it's abbreviated as KM. Yeah, they use kilometers. In this country, we use miles. Canada, they use kilometers. Meters. Meters are used all the time, abbreviated as M. Have you ever heard of millimeters? Millimeters? If you go into nursing, you'll hear of millimeters. Millimeters. Okay. These are typical units of length in the metric system. And you know, the beauty of the metric system, ladies and gentlemen, is that it's so much more streamlined and efficient than our ugly English system of measurements. The metric system is based on powers of 10. And so it's very, very easy to compute within the metric system, as opposed to our ugly English system, where we have to use these awful unit conversion factors. Let me show you the metric system for length. All right, now the metric system goes like this, ladies and gentlemen. We have what's called a base unit. A base unit is a magnitude of 1, or has a measure of 1, base unit. 10 times smaller than a base unit is called a deci unit. Deci, that's the prefix. It's 1/10 the size of a base unit. 100 times smaller than a base unit is called a centi. Centi unit. The prefix is centi. It's 1/100th the size of a base unit. 1,000 times smaller than a base unit is called a milli unit. Milli. It's 1,000th the size of a base unit. 10 times larger than a base unit is called a deca unit. Deca is the prefix, 10 times bigger than a base unit. 100 times bigger than a base unit is called a hecto unit. Hecto, 100 times bigger. 1,000 times bigger than a base unit is called a kilo unit. Kilo, 1,000 times bigger than a base unit. Megabytes on a computer. Mega, ladies and gentlemen, is 1,000,000 times bigger than a base unit. Gigabyte of memory on the computer. Giga is even bigger. I'm running out of room, but ladies and gentlemen, giga is the prefix that represents 1,000,000,000 times bigger than a base unit. Then you even have a tera. Anybody have a computer that has terabytes of memory? Tera? A tera is 1,000,000,000,000 times bigger than a base unit. 12 zeros. Everybody see this here, ladies and gentlemen? It's called a metric system in general. These are the prefixes of the metric system. And as far as length is concerned, in particular, the fundamental base unit of length in a metric system is called the meter. M for meter. 10 times shorter than a meter is called a decimeter, abbreviated as DM, decimeter. This is the base unit. This is the deci. 100 times shorter than a meter is called a centimeter, CM, abbreviation. 1,000 times shorter than a meter is called a millimeter, MM is its abbreviation. See that there? 10 times longer than a meter is called a decameter, DAM, short for decameter. 100 times longer than a meter is called a hectometer, HM, hectometer. 1,000 times longer than a meter is called a kilometer or kilometer, KM. Is this making sense here with the metric system so far, ladies? Now, it's very easy to compute within the metric system. It's actually a piece of cake. For instance, ladies, if I gave you, let's say that the distance between my home and the road is, let's say the distance is 123 meters. And I want to convert 123 meters to kilometers. It's a very, very simple thing to do. We don't have to string together any messy conversion factors like we do in converting in our English system. All we have to do, ladies, I'm going to shift we just have to shift the decimal point, because I indicated the metric system is based on powers of 10. The base unit, ladies, is 1 is really 10 to the 0th power. 10 is 10 to the 1st power. 100 is 10 to the 2nd power. 1,000 is 10 cubed or 10 to the 3rd power. A deci unit, 1/10, is really 10 to the -1 power. Centi unit is 1/100th, which is 10 to the -2 power. Milli is 1/1000th, which is 10 to the -3 power. So you can clearly see that the metric system is based on powers of 10, isn't it? See that, ladies and gentlemen? So the way it works is this: to go from meters to kilometers, ladies and gentlemen, if you have this written out on your paper from left to right in this order, kilometers, hectometers, decameters, meters, decimeters, centimeters, millimeters, then all you got to do on your paper is go like this. We want to go from meters to what? Kilometers. So I have to move my decimal point 1, 2, 3 places to the left. That's all I got to do. Just shift my decimal point 3 places to the left, because that's equivalent to as if I really divided my meter measurement not by 10, not by 100, but divided it by 1,000. So if I divide this by 1,000, the decimal point is going to get shifted 3 places to the left. 1, 2, 3, and there's your answer. So ladies and gentlemen, 123 meters is really 123,000th of a kilometer. Everybody see how I just converted meters to kilometers by shifting the decimal point 3 places to the left. So if I have 273.5 hectometers, ladies and gentlemen, and I want to convert that to, let's say, decimeters, how would I do that? How do I convert hectometers to decimeters? Well, I put my pencil here and I go from hectometers to decimeters. I got to shift my decimal point 1, 2, 3 places to the right. That's equivalent to as if I multiply my hectometer measurement by not by 10, not by 100, but multiplied it by 1,000. That'll shift the decimal point 3 places to the right. 1, 2, 3. I got to add 2 zeros. 273,500. Ladies and gentlemen, I just converted 273.5 hectometers into decimeters. Is that making sense? That's all there is to converting in the metric system. It's just a matter of shifting your decimal point to the right or left. Once you have this scale written out on your paper from left to right. Everybody see that there?
Mm-hmm.
That's all there is. You got to love the metric system. It's very easy to convert in the metric system. So I'll tell you what, for classwork number 3, let's see if you can do a couple of problems here. Let's see if you can do problems 21 22 and 23. I want you to convert in 21, 248 meters to kilometers, 22, 969 meters back to kilometers. And 23 is 67 centimeters to millimeters. See if you can do those conversions here.
You said 21 and what else?
Yeah, you know what? Let's do 21. I don't want to do 22. It's a repeat. Let's do 21, 23, and number 25. We'll call this classwork number 2. 21, 23, 25, okay? 21, 23, and 25. I would like you to do those conversions in the metric system. Does anybody need to see my scale? Just write those. Well, you want to write them down on your paper quickly, or do you have a book where I can show my scale on my paper? Or can you guys see my doc cam? It's kind of small now, isn't it? Kind of small.
I
See,
took a picture.
I wanted to go back and show you this scale to aid you in converting, but then you'd have to remember what the problems were, 21, 23, 25. You may not have written them down. So do we have the scale written down here, Lisa? Just write that scale down first, and then you can go back and do your problems, okay? All right, so I'll go back to the book then. All right, 21, 23, and 25, do those right there. Okay. So 248 meters converted to kilometers. We put our pencil here on meters, and we got to move our decimal point 1, 2, 3 places to the left. So that's equivalent to as if I divided my meter measurement by, not by 10, not by 100, but divided it by 1,000. That's going to move the decimal point 3 places to the left. So the decimal point's understood to be to the right of the 8 here. 3 to the left, 1, 2, 3, 0.248 kilometers. Anybody get that one correct?
Yeah, correct.
All right, we're good on that?
Mhm.
All right, and the next one is this one, number 23, 67 centimeters. We want to convert to millimeters. Simple thing to do. Put your pencil on centimeters, and we have to just move the decimal point 1 place to the right to go to millimeters. That means we really have to multiply our centimeter measurement by 10. So that shifts the decimal point, which is presently after the 7, it shifts it 1 place to the right, which means we have to add a 0. So that would be 670 millimeters. So 67 centimeters turns out to be 670 millimeters because we shifted our decimal point 1 place to the right.
To the right. I did to the left.
Yep. That's why you want to have the scale in this order so you know which direction you need to go. So always have it in this order from left to right here. Finally, 3,498 centimeters, we want to convert to meters. So we want to go from centimeters back to meters. So we have to shift our decimal point 1, 2 places to the left. Do you agree? To go from centimeters back to meters. That's equivalent to as if we really divided our centimeter measurement by, not by 10, but divided it by 100. All right, 2 places to the left, the decimal point, which is understood to be right here. 2 to the left, 1, 2, that puts it between the 4 and the 9. 34.98 meters is equal to 3,498 centimeters. Do we understand how we're converting in the metric system, ladies and gentlemen?
Yes.
It's just a matter of shifting the decimal point. You know, the beautiful thing about the metric system is these prefixes never change. What changes is what you're talking about. Today, we're talking about units of length. Next week, we'll talk about units of what weight. We'll talk about this as being the what? This is being a gram, decagram, hectogram, kilogram, decigram, centigram, milligram. Do you agree the units remain the same? These units, these prefixes, they don't change. Whether you're talking about length or weight or volume units, doesn't matter. The prefixes always remain the same. If you're talking about volume, you'd be talking about, this would be liters, decaliters, hectoliters, kiloliters, deciliters, centiliters, and milliliters. So the prefixes never change. That's the awesome thing about the metric system, because it's based on powers of 10. It's so easy to convert in the metric system. It's just a matter of either dividing by an appropriate power of 10 or multiplying by an appropriate power of 10, depending what direction you're converting towards. Or it's just a matter of shifting your decimal point, therefore. Correct? All right, that's it. I'm out of material and I'm out of time, ladies and gentlemen. If you can just get those classworks to me, that'll be good. I will eventually get a chapter, a quiz number 3 to you for chapter 6. I'm almost done grading all of chapter 2 quizzes, and I'll record those. Okay, ladies, I'm just trying to stay up with the homework because I don't know. It just seems like the pace of this class is quite intense. Don't you agree? But you know, you stop and think, February 1st is next, what, Tuesday already? This Tuesday coming up, isn't it? Do you realize we only got 1 month left of this class? That's it? This thing's over in March, what was it, March 2nd or something?
Mhm.
I mean, we only got a month. You know what I'm saying? So unfortunately, we got to cover quite a bit of material per session. Unless there's any other questions, you guys have a great, safe weekend. Hopefully I'll see you next week. I'll stay on the line for a couple minutes.
So you're releasing the quiz today or tomorrow?
I will, yeah, I'll try to get it out today. If I don't, it will be by tomorrow morning, okay?
Okay.
Yeah, because my schedules on Thursdays are just crazy.
And that's due Monday at
Monday
11:59?
midnight. Yeah, 11:59 p.m. on Monday. All right, now I'll make it official with an email, okay?
All right, thank you.
All right, yeah, have a good one. Any other questions or concerns, Jennifer? All right, if not, I'm signing off.